Very good. So most of this talk is based on a paper with my amazing PhD students, Lee Kayua, as well as Christophe Duc. And it appeared at S&P this year. So as you know, distributed systems like blockchains are based upon different various layers. So some of these layers at the very bottom, you might think of the hardware layer, where there's the CPU, which is like maybe here at the lower end. But there's also the network layer. There's the consensus layer, or the way that you build the consensus, as well as an application or logic state. And we have seen many things coming out of this beautiful construct of decentralized systems, as Gün presented in his talk earlier. And some of them are mostly focusing on finance, whereas there are also a lot of non-finance applications, obviously, which are very important. But in this talk, we'll be mostly focusing on the finance aspects, specifically those that are called DeFi, or decentralized finance. And one interesting property that we can see is the atomic composability of transactions across different protocols, whether these are swap or exchange protocols, lending protocols, new concepts such as flash loans, etc. Beautifully, the community actually developed standards that everybody can use, that everybody can follow. So developers basically follow the very common asset standards, such as native coins that are native to the blockchain, as well as fungible or non-fungible coins. On the other hand, we have certain market mechanisms that are actually quite mirrored from the traditional centralized finance, such as the concept of arbitrage. So that's the concept of, like, if a price goes up or down in a remote market, then an arbitrageur can try to equilibrate or synchronize the prices among different exchanges or among different markets. If there's a lending and borrowing protocol, we have liquidations, we have governance mechanisms, and collateral or security deposits. Well, all these beautiful techniques, they unfortunately don't exist without manipulation. In particular, market manipulations are quite transparently performed in these decentralized systems, because everything is transparent. You can read the ledger, you can listen on the peer-to-peer network. So we're seeing a plethora of adversaries performing front or back running. We've seen many pump and dump attempts. There are beautiful papers outlining them. We have beautiful papers on wash trading. And there are other more traditional techniques that might occur, like market cornering or gear rating. It's not always clear whether these are actually financially rewarding, but this is a war out there, right? On the blockchain layer, basically, on the blockchain peer-to-peer, as well as on the consensus layer, there's an ongoing war between traders. So you might ask, but why do we need a decentralized exchange? And this really goes back to the core idea of what Gün just said. We want to have systems that are decentralized. We want to avoid gatekeepers, right? So let's assume we have Alice, who is a whale. She wants to provide her money to traders to earn fees. But she doesn't want to trust anyone to manage her money. So she has not really an option to give her money to a bank, which is a centralized entity that then manages her assets. On the other side, we have Bob, who is a nifty trader. He wants to buy the latest coins. He wants to sell them at any point in time, whether the bank is open or not, right? So he wants to have freedom. And what's also important to Bob is that he remains custodian over his assets. So he wants to be able to transfer his assets or tokens at any point in time. But Bob struggles to find a trusted source to buy any coins, or maybe the bank is closed, or his broker is currently on holiday and cannot perform the trade that he would like to do. So that's why decentralized exchanges, or DEXs, are effectively implementing the exchange mechanisms that you can find in centralized finance on blockchains, specifically in a smart contract. So the three main components that we need is a price discovery mechanism. So you might have heard of a limit order book in traditional exchanges such as Binance, the Nasdaq Stock Exchange, etc. There's a trade matching that you need to have, and there's a clearing that's required to happen, right? So once Alice and Bob, they have orders that match, then we want these orders to resolve each other and to be cleared, meaning the coins should change from one wallet to the other. So the swap should happen on chain, ideally atomically, because we don't want that somebody loses its coins. So if you look at the history of DEXs, they have been growing significantly in the last years, especially beginning of this year here. So you can see the latest months. And it's interesting. So most of the volume actually goes to Uniswap. So this is the Uniswap color. But we do see quite a variety of different protocols, which is great, right? So we not only have decentralization in terms of assets and custody, but we also have some kind of a diversity of various protocols here. So even the daily volume, so if you look at the 24-hour volume, DEXs are not yet there where centralized exchanges are, but they're getting there, right? I mean, they're growing quite significantly. So which is quite interesting. A note of caution here. So if you compare just the numbers of DEXs and Binance, for instance, we don't know to what extent centralized exchanges perform wash trading. I'm not saying that Binance does. It's just there's no fundamental proof that they don't, right? It's really hard to kind of quantify whether a centralized exchange does wash trading. So wash trading is the process of buying and selling a token or security just in order to inflate the trading volume. Whereas on DEXs, if you want to perform wash trading, you can do that, but you will need to pay transaction fees such as gas, which is costly. So it's not for free. It doesn't come for free. All right. So in this talk, we basically will go into more details about sandwich attacks. In order to understand sandwich attacks specifically, we have to dive a bit deeper into the blockchain peer-to-peer network. So the very traditional peer-to-peer network since Bitcoin is basically where we have a set of miners all over the world. We have a transaction that is propagating here, and there's a certain fee that was specified. So there's a mempool. So we have here this mempool. Let's say there are 2 transactions already in this mempool. A third transaction comes in, and it then slips here in the middle because miners are supposed to order transactions according to a descending gas price. So eventually, if a miner mines this block, the order of a block should be as such, and the execution order is also that way. So an adversary might connect to any node in the peer-to-peer network, and we have seen peers that are heavily connected. They have like very good internet connectivity with low latency and in many parts of the world, and are trying to get information as soon as possible that might hit the peer-to-peer network. So if an adversary now is connected to, for example, this entry node here, which receives the transaction from the user, then this adversary could perform a so-called front-running transaction, whereby the adversary issues a transaction with a slightly higher gas price, and then is hopefully able for the adversary to jump in front of the victim transaction. So that's referred to as front-running. The same can happen with backrunning. And in the backrunning case, we have both the victim and the adversary transaction paying a 5 gas fee in this particular example. Why the same amount? Because the miners, they are supposed to, depending on the software obviously that they run, they're supposed to have a FIFO queue for those transactions that pay the same transaction fee. So these are very standard techniques, front and back running. So given this knowledge, you can understand obviously how transactions are propagating. There are a few alternative propagation designs. So you can, for example, have a direct connection to the miners, right, where you send your transaction and they will try to mine it, so it won't be broadcasted. There are also relay services where you can send your transaction directly and they send it to the miners It's also an option. Some blockchains claim that they have private mempools. I'm not yet sure to understand how those work. I would be quite curious how this would work in general. And there might be faster blockchains where this front-running game or back-running game might be trickier, because we know that latency, for example, the longest latency on Earth between any two places is probably on the order of, I'd say maybe 100 milliseconds, depending on glass fiber speed. So between Europe and Australia, I think it's about 100. So it's unclear how well front-running works if the blockchain gets much faster, or yeah, how this evolves. I mean, this is basically an open research question. So, okay, now we know what the peer-to-peer network is about. What about automated market maker? So how do they operate? And why would they be vulnerable to so-called sandwich attacks? So an automated market maker, or the basic idea of an AMM, is that we have a smart contract who does the market making. So we have a big pool of assets, X and Y here. And Alice, as you remember, maybe is the wealthy individual who would like to contribute some liquidity, like for asset X and asset Y. And then there's Bob. He would like to trade X for the asset Y. And he will also pay a small fee to Alice to incentivize Alice to actually provide liquidity into the smart contract pool. The very basic formula for performing such market making is the so-called constant product automated market maker. Constant product because the asset quantity of X times the asset quantity of Y is equal to a constant. And this very simple formula yields interesting properties such as you can get instant liquidity irrespective of the trade size. Naturally, if you purchase a large amount, you're pushing the price down or up significantly. So it is instant at a cost. You can purchase so if you purchase an asset X, you increase the price of X, whereas you decrease the price of Y. And what's interesting, you have this pool, right, with the asset X and Y here, and the ratio, so the quantity of the liquidity in this pool is actually sets the price between those two assets. So if you plot this on the graph, you get this so-called bonding curve. So in the initial state here, we have 30 coins of the asset Y, and we have 10 coins of the asset X, right? So the constant is 300. Now, if let's say we remove, we do minus 10 coins of Y. So we basically want to get 10 coins of Y. How many X do we need to provide to the pool? Can anybody tell me that? Any idea? So we remove 10, so we get here to 20, right? So it will be something like this. So how many here, how many X do we need to add? The answer is, okay, I'm gonna tell you. The answer is 5.
There are answers in the chat window.
Oh, sorry, I didn't see it. Very good. Yeah, 5. Oh, multiple times. Okay, sorry, I didn't see the chat. Yeah, perfect. It's 5. Correct, because the constant is always 300, right? Okay, so now we understand the basics of an AMM. So any trade is basically really like moving along this bonding curve, right? So you start here and then you move along towards another price state. So this means that you have an expected slippage. Expected slippage is the expected increase or decrease of a price, right? So if you buy a certain quantity, you know by how much it will move. And now the problem is that there's also an unexpected slippage. And this unexpected slippage is the one that's realized just before your transaction gets executed. because you're, for example, being front run. Now, it can also happen that you get a better execution price because the market actually moved the other way and your transaction got executed just after the market moved. So there's this asynchrony or this information asymmetry between the state at which you create a transaction and the state at which your transaction is executed. So to protect yourself from this asymmetry, you have basically an option to protect yourself with a slippage. So that's a kind of a circuit breaker in traditional finance, whereby you stop or you let the transaction fail if you reach that slippage. So you cannot cross this, right? So if the unexpected slippage is too significant before the execution of your transaction, your swap will not happen. Well, that's enough information for us now to jump into sandwich attacks. Sandwich because we have two adversarial transactions, at least two, which squeeze the victim and produce this juicy sandwich where the victim is the nice meat in the middle. So you have a first transaction here that pushes the victim slippage to the maximum, but not beyond. That's important. And then the adversary can exit its position by selling the asset again. So you can also visualize this here a bit in another way. We have here block N and the block N+1 or N+K, depending on how many blocks we succeed in the attack. And you have here the victim transaction TV, right? And it's being sandwiched by adversary 1, adversary 2 transaction in the execution order, which should be this one. So the sandwich attack system basically looks similar to this. So you have a victim, right? So he sends a transaction, broadcasts it in the network. Everybody sees this transaction, and especially the adversary here with the spy node. The transaction is then added to the adversary might attack the transaction if it's profitable, and then he broadcasts his 2 adversary transactions, and the miner in the end will include those 3 transactions. Maybe in the same block, maybe in different blocks, doesn't really matter. Just the sequence needs to be in that order, A1, V, A2, for the adversary to profit from that particular transaction. So what's interesting about this is that when you plot, for example, if there's a victim that performs a trade, let's say we have a victim that performs a trade of 20 Ether on this particular Uniswap block, Uniswap market at block 9 million, which is like about, I think, a year and a half ago. Then you can see here that an adversary is actually most of the time not profitable, right? Red is a loss for an adversary. So they are not all of the trades that a victim does on an AMM are profitable to, or are I mean, not for all trades, an adversary will attempt a sandwich. So ideally, I would really want to see some improvements on the AMM UIs, whereby users are being warned that your trade is fine, it will not be sandwiched, or your trade might be sandwiched because it's the volume is too big or the slippage is too high. So I think there's still some, we can still perform some usability improvements on that end. So the sandwich I just presented was where a liquidity taker attacks a liquidity taker. There might be other cases where a liquidity provider can attack a taker. So you can think of an attacker actually removing liquidity here. So this actually moves the entire bonding curve. Then the victim executes, then the attacker adds liquidity and performs a sale. So there might be settings where providers are incentivized to remove or add liquidity to exploit victim transactions. And I give it to you for future work to be as creative as possible, maybe to come up with new examples of how to design sandwich attacks or similar manipulation techniques. So I mean, this example was particularly striking to me because I always thought that the liquidity provider is incentivized to keep its assets in the pool to gain transaction fees. but at times that's actually not probably not correctly parameterized, such that such attack becomes profitable. So what can we do to protect users? Some people, or I propose to use the Starlink network as a relay network to increase transaction speeds in the blockchain. Obviously, that's not a great idea to protect against sandwich attacks, because then we have a centralized entity that can perform a lot of sandwich attacks. So that's not a good idea. But there might be other good ideas. So ETH Zurich here implemented mitigation using this minimum profitable victim input, or MVI, by splitting a transaction into like a swap into several transactions. So you can see this tool here. So the cool thing about this idea is that you can effectively be sure that a rational adversary should not attack you. There still might be irrational adversaries out there, you don't know. And the drawback is that you have to split your trades such that you can't execute them one by one. So you need to distribute them across blocks, across market changes, which is quite cumbersome. So more viable solutions are necessary. So one promising avenue, I think, are fair ordering techniques. So the family of Equitas protocols from Ari, which actually might be a technique to render any consensus protocol fair. Fair in terms of order, fairness. It's defined in their paper. And I also think we need better user protections or UI awareness warnings for users. You might be sandwiched now, or you might not be sandwiched. Just more education in the DeFi space, I think, is really key. So what about multiple attackers? So we've tried to simulate what happens if there are multiple adversaries attacking a particular victim. So the more adversaries there are, the less profitable the game becomes for the adversaries. So this is at least our result, right? So you can see here, with 10 adversaries, technically the gas price really becomes very high. So, and this is where private bidding relay services change the game quite significantly. But this is at least if we play on an open peer-to-peer, on an open and decentralized peer-to-peer network. Very good. If you want to learn more, we are starting a DeFi MOOC in the fall. It's an open DeFi MOOC. We'll be happy to go deeper into sandwich and also other market manipulation attacks. And yeah, happy to hear your questions.
Any questions for Arthur? You can use the chat window, or you can unmute yourself and ask directly. Okay, well, a very lucid presentation. Oh, here we go. There's a question somewhere in the chat window here. Ah, okay.
Do AMMs fundamentally depend on the existing of external exchanges? Is that the question? I suppose so, right? From
I think that's the question, yeah.
From Sergey, right, perfect. On the existence of external exchanges, they don't depend on it, but there's an inherent link between external exchanges and like centralized exchange and blockchain-based exchanges, in the sense that if they share the same assets, they will be arbitrageurs, so entities that trade on both markets and which try to profit from this price spread between those markets. Meaning, if the price on one exchange is higher than on the other, then they will buy it at the lower priced exchange and sell it on the higher priced exchange. Right? So there's no implicit dependency, I would say, but there's an implicit link once they share the same assets. You continue with your question, like if Uniswap, if the Uniswap exchange rate goes out of sync with Binance and arbitrageurs brings it back, but what if there's no Binance? If there's no Binance, then let's assume there's only one Uniswap market that hosts two assets that are not hosted anywhere else. then you can still trade between those two assets on Uniswap, but there would be no arbitrageur equilibrating the price on other exchanges, right? So overall, it's an interesting setting because you will have less overhead trading or arbitrage trading, but you can still use this particular Uniswap market and trade those two assets in isolation, right? That's perfectly fine. And you can actually do this, right? You can create your own Uniswap market. You can create two random ERC tokens and just put them on this market. There's another question from Leland. So how do sandwiches ensure that their transactions is prior and directly after the swap? Have to use something like flashbots. So they don't have to use something like flashbots. So flashbots is a relay service. But as I mentioned here earlier in the slides, they can do this front and back running, right? So here you can see that they can, if they pay a higher transaction fee, right, 6 instead of 5, which is the victim in this particular example, then this is the victim. Then the adversary here will be executing it in front of the victim if the execution order of this block is in this direction. And similarly for backrunning, if they pay the same fee or the same fee or lower fee, then they would execute after the victim transaction. That's typically referred to as backrunning. So you can perfectly position yourself between like in front and behind the victim. So we measured this. I think about 80% of the miners followed the gas price priority. So in expectation, 80% of the cases you are successful by setting these gas prices. Now, Flashbots is a completely different game, right? This is not playing on this open peer-to-peer network. It's a centralized server that has private peering agreements with miners. And in there, you create so-called bundles where you take as input the victim transaction, and you prepend your front running, you postpend your back running transaction, and you send this as a bundle to the Flashbots miners, and that's how you basically guarantee the order there. Could you elaborate on whom and how exactly backrunning harms? Oh, that's a great question. So backrunning in the sandwich attack model is basically a way for an adversary to exit a position, right? So if in the first transaction you purchase an asset, then the victim purchases the same asset, and then in the third transaction, so the second victim transaction, you exit the position. This means that the adversary is realizing a profit, right? So that's specifically for sandwich attacks. To answer your question more broadly, backrunning is quite detrimental to the health of the blockchain peer-to-peer network, because in the blockchain peer-to-peer network, we have actually witnessed backrun flooding, whereby an adversary might send many transactions with a same or lower gas price as the victim, and flooding the peer-to-peer network. So backrunning is quite painful, is quite detrimental to the health of the information dissemination protocol of the blockchain, which means that if you have flooding on the network layer, you have less communication bandwidth, you have more stale block rates because everything becomes slower, and this in the end deteriorates security of the entire chain. So it's quite bad. Yeah.
Okay, well, you have a flood of questions in the chat window, but we should wrap up here. So perhaps you can take those offline, perhaps
Perfect.
even in GatherTown later if you have time. Let's thank Arthur again for his presentation.
Thank you, everyone.
Thank you.